Hey everyone, so this is the code that we worked with in the last video. Let me just get rid of this and this as well. Now what I want to do is I want to print the size of my complex number, and notice that I've changed this to a complex number instead of a pointer. So I do printf %d and then size of z1, and let's try running this. As you can see, it gives me the size as 8 bytes, which is expected because this first int that I have will be 4 bytes and the second int that I have will be another 4 bytes. So 8 bytes does seem correct for this. But let's try doing something like a char c1 here, and now I know that this is 1 byte. So my expected size is now 9 bytes, so my output should be 9. Let's try running this, and as you can see, it gives me 12 as the output. So somehow this struct has suddenly become 12 bytes, whereas I was expecting 9 bytes. And the reason is as follows. So in a 32-bit machine, when there is a memory read, so when some value is read from memory, it reads 4 bytes at once. So what it will do is, let's say it has a location 0. When it wants to load something from the location 0, it picks up locations. So byte 0, byte 1, byte 2 and byte 3. It picks up all 4 of these together. Because of this, so to improve efficiency in such a system, the architecture enforces that our ints should always be placed at 4 byte boundaries. So I cannot have an int that starts at byte 1. It will always start at either byte 0 or byte 4 or byte 8 and so on. So what happens is, when it's storing into memory, it stores C in the 0th location, and then it keeps 3 locations empty, and then it stores my real in 4 locations. So this is let's just use RE to indicate that this is using up 4 bytes, and then I'll have my IM, which is another 4 bytes. So in total this takes up 12 bytes, and that ensures that when it's reading from memory, it reads either this part or it reads this part right here, which gets it the real number. If it had done something like this, when it was trying to read the first character, it would have read some part of the real number but not the entire thing. So because that becomes complicated, it just adds a padding. We call this a padding that it adds, and it makes sure that any integer is always at a multiple of 4 location. So that's how the size of struct works. And what I can do is, another thing that I want to test is I add a char c2 here. Now this is 1 byte again, but again this is going to have a padding. Now there are 2 things that could happen here. One is, if the struct is allowed to rearrange its members, what it will do is it will do something like this. It will say C1, then it will do a C2, and then it will do an RE. Actually, let's just use 1 and 2 for this, because these are just 1 byte, so there will still be 2 blanks. Then there will be RE, and then IM. And this is how it should be if the struct is allowed to rearrange its members, and that would give me a size of 12. The other possibility is it does 1 and then 3, a padding of 3 bytes, and then RE, and then 2 and then a padding of another 3 bytes, and then IM, which would give me the size as 6 bytes. So let's just try it and find out which one it actually gives me. So let's go ahead and do this. And as you can see, it gives me the size as 16, which means that within a struct, it's not allowed to rearrange the members. So if I have a C1 first and then an integer and then another character, it cannot put this character in memory before the integer. It has to follow the same order. That's how the syntax is, and that is again related to cases where what a struct represents is beyond just this program unit. So basically what you need to remember is within a struct there cannot be any rearranging of the members. So that's the second thing you need to keep in mind when working with structs. If I move this one right here to here now and I try running it now, it's going to give me the size is 12 because this time it was this memory allocation that it followed, the char 1, then the char 2, then a padding of just 2, then the real int, and then the imaginary int. So that's the second thing. Now what I'm going to do is I'm going to get rid of this right here, and if you remember, this one was 12 bytes, but what I'm going to do is I'm going to change this to a double, which is 8 bytes this time. And now let's go ahead and run this. So this time what I expect is it will have my char, then it will have a padding of 3, then it will have RE, and then it will have IM, and the size I expect it to be 16 bytes. So let's just go ahead and try it. And it does indeed give me 16 as the size. Now what I'm going to do next is I'm going to change this to a double as well. So this is another 8 bytes. And this time what I expect is a C, then 3 blanks, then RE for 8 bytes, and then IM for 8 bytes. And my size comes out to be 8 of these plus 8 of the imaginary, that's 16, and plus 4, 20. Let's try this now. I expect the result to be 20. But as you can see, this time it gives me the result as 24. So what's going on now is that the architecture again this time plays a role here. So it enforces that for a double, which is 8 bytes must be at an 8 byte boundary. So it could be at 0. The next place where a double could be is 8. It cannot even start at 4. And then it will be at 16 and so on. And in a 32-bit machine, because it reads 4 bytes from memory at a time, it would take 2 memory reads to get a double. But in case of a 64-bit machine, it fetches 8 bytes at once. So a double can just be fetched in one go, which is why the size of struct becomes 24 in this. So it gives, instead of just a padding of 3, it gives a padding of 7 right here, which makes the size 24. So that's about calculating the size of structs, and I think this is a very important concept which you should know. If you say that you know C language well, you should know what the size of a struct is. So that's it for this video, and this concludes our discussion on user defined data types. I hope you like these videos, and I'll see you next time.